Okay, so hello everybody, and thank you for joining our talk. Today we are going to share with you some unique insights about one of the most sophisticated espionage tools in the world, the Kazuar Backdoor. But before we begin, let us introduce ourselves.
Yeah, I don't need the clicker. Hi everyone, so my name is Daniel Frank. I'm the team lead of Cortex Threat Research. And it's actually my second time in Sweden, so I'm really excited being here, so thank you for having me. I also work with this guy.
And my name is Tom Fakterman. I'm a senior threat researcher for the Cortex Threat Research team in Palo Alto Networks. And this is my second time presenting here, so this is really exciting, so thank you for having me back. So what do we have for you today? We will start with some background about this malware and all the operations behind it. After that, we will dive into our analysis of Kazuar and see what kind of challenges we face trying to pick apart this malware. We will talk about its architecture and core functionality, what cool stuff it can do. After that, we will talk about how to catch a Kazuar. Basically, what can we do to detect it? And for the end, we will leave you with some key takeaways that we have from this research. So let's begin. So let's start with some background about Kazuar and all the operations behind it. Kazuar was initially discovered by Unit 42 in 2017. It is an advanced and stealthy .NET backdoor. And since its initial discovery, it was only observed to be used in very selective espionage operations that mostly targeted organizations in the European government and military sectors. Now, Kazuar is known to be part of the arsenal of tools of a Russian APT group, known as Turla, or as we track it in Unit 42, Pensive Ursa. The US government attributes the activities of Turla to a unit within the Russian Federal Security Service, or FSB for short. Basically, this group is considered to be one of the most advanced hacking groups in the world. And since its initial discovery, Kazuar has remained under constant development. But since 2021, there was a 2-year period where it was not seen in the wild. And let me give you just one fun fact about Kazuar. Kazuar is a Russian word for cassowary, which is a large flightless bird that is native to Australia. So if any of you wondered how a Kazuar actually looks like, here is a picture. Now, our story begins in July of 2023. The Ukrainian CERT published a report that described targeted attacks against defense forces for the purpose of espionage. And in this report, they described the use of 2 main malware. The first one is named Capybara, which is an exchange server backdoor. And the second one is a new variant of Kazuar. And as you have already realized, today we are talking about the latter. And in this report, they attributed those attacks to be the work of Turla. So when we first read this report as a research team, we were really excited to get our hands on this new variant, to try and pick it apart. So we tried to search if we can get our hands on this new sample. But unfortunately for us, it was not uploaded to VT, or anywhere else for that matter. It was not publicly available, which made us really sad. But maybe the stars were aligned just right in the sky, because we got kind of lucky and we actually managed to find that very same sample in our own internal telemetry, which of course made us really excited. So we immediately started to analyze this new variant of Kazuar. And very quickly, we were pretty amazed with what we were dealing with. For example, we saw very impressive host data collection capabilities, which we'll expand more upon later, but basically it can collect everything from the infected machine. It can receive, it has a unique set of 45 commands it can receive from the C2. It can use several different techniques for anti-analysis and evasion. It has layers of encryption and obfuscation, and many, many more cool stuff that it can do. So now, without further ado, let me pass the stage to Daniel to talk to you about our analysis of Kazuar.
Thanks, Tom. So obviously, when dealing with such a robust and such a complex malware, we had to face some challenges in analyzing it, right? Like, couldn't be that easy. So let's review these challenges. First of all, a lot of code. This was quite a big sample in terms of malware. So we had thousands of lines of code and like code lines and classes and whatnot. And of course, nothing was just like plain text. Everything was, the strings were obfuscated, the variables and classes names did not have any meaningful names whatsoever. So it was just like a whole big chaos. And on top of that, the Kazuar authors implemented multiple encryption algorithms. So we also had to face the challenge of trying to decrypt different data from disk. So starting to actually solve these challenges, we kind of took the approach from going from the easiest challenge to the most, you can say, difficult challenge. So in terms of obfuscation, the Kazuar authors implemented a really simple Caesar cipher, which is, as most of you probably know, it's basically just swapping one letter for another. But what they did was implementing hundreds of different Caesar cipher instances. So it was really annoying. But what we did was we opened the malware, it's a .NET malware, we opened it in the NSPy, extracted all of these C# source code files, and then we wrote the script that just located all of these instances of the Caesar cipher and just rewrote it straight into the source code files, rewrote the results. And what we were started to see in this point was mainly Kazuar's really verbose logs. So we started understanding a little bit what the malware was doing. Second thing was, and this was more of a manual labor, was renaming classes and methods. So this is an example for a method that handles encryption of some sort. And as you can see, there are no meaningful names except the library functions. So what we did was we just opened the whole project in VS Code. We installed the C# plugin, and the C# plugin allowed us to change these names in bulks. I mean, like when we did one change, it computed all of the cross-references, and then it renamed all of the remaining instances of this method or another as well. So we were able to get from what you see on the upper left-hand side to what you see on the bottom right-hand side, and continue and understand the functionality of the malware and keep renaming and renaming these methods. Last but not least, this is an example of how a log file, I think, of Kazuar looks like on disk. So we also, of course, had to either intercept the encryption process or just understand the algorithm and decrypt it from disk, and to get from this to this. Once we were able to do that, we had another interesting glimpse of how well organized the code is and how the Kazuar authors logged all of their activity. You can see that they documented the thread name, the execution time, where the malware was injected to, etc., etc. So it was really cool to see. And this is an example of a Kazuar decrypted configuration file. So the configuration file provided us with some really valuable insights. For example, the internal versioning of the malware, the C2 servers, the injection modes, which we'll talk about in a second, features that were enabled or disabled, and other interesting and valuable data. The next thing I would like to talk about is Kazuar's architecture. So as I said, really professional software engineering principles were implemented in this malware. It was really cool to see. And I would like to review some of them. So what are these injection modes? So Kazuar has 6 distinct, what we called, and they called as well, actually, injection modes. So each injection mode is basically responsible on a couple of things. So first of all, what process should Kazuar be injected to? So Kazuar is a really stealthy malware. It doesn't operate as a standalone executable. It is like every time it's just being injected to this process or another. And Kazuar has also the ability to either communicate with the command and control server using HTTP or communicate with other Kazuar nodes on the network via named pipes. So the injection mode also kind of decides which feature is turned on or off. Tom will later talk about these HTTP and and proxy modes, and what other general functionality should be turned on or off. Each injection mode had its own unique features. Also, the Kazuar authors implemented a multi-threading model to obviously handle a lot of tasks simultaneously. So they, again, really organized, named each thread, and each thread was kind of responsible of a major operation that was taking place on the infected device. So they had event log monitoring, an anti-analysis thread, and also the active window monitoring thread, which they, I don't know, it was a little bit funny to me that they called it PEEP. Took a time to figure out what this thread was doing. And maybe you noticed that we're missing two other threads. So these are kind of the backbone of Kazuar. These are the task solver and the sender threads. So these two threads are responsible of sending data to the author's command and control server and receiving what Kazuar authors called new tasks, just new things to do on an infected device from its operators, execute commands, download files, or whatever they feel like doing. And if we will deep dive a little bit into this task-solving mechanism, so we will see, first of all, the components, which is the command and control server, the sender and solver threads, a task file and the results file. Both are encrypted, obviously. So how it works is pretty simple. The sender thread reads a new task from the command and control server, writes task into a task file. Then the task solver thread waits for these new files to be written. It will read the task, execute whatever desired command it received from the task file, write an encrypted results file, then add another layer of encryption to this file, and send it back to the C2. Cool. Now, allow me to geek out for a second, because I think this is the right conference to do so. So this is like, in general, how a Kazuar results file looks like. They have sort of a delimiter, a unique identifier, UUID length and content, which are also encrypted. Kazuar uses different manipulations on the machine's UUID to create different encryption keys and different identifiers. And it uses a sort of hybrid encryption. It encrypts the task using AES, but it also encrypts the AES and the initiation vector using a hard-coded RSA key. So, yeah. Now, looking at this task-solving mechanism, we kind of noticed that this looks familiar. So different reports by CISA and other vendors as well said that Kazuar is the successor of Carbon. So Carbon is another backdoor that was previously discovered in 2017 as well. And CISA mentioned that Carbon is a fork of Snake. I don't know how many of you read it was a really big report in 2023 about the Snake malware. It was a really super sophisticated malware by Turla. So in terms of attribution, it was really cool for us to see all of these similarities and see for ourselves like how Kazuar is similar to Carbon and Carbon is a fork of Snake, and like seeing this really cool developmental process by the threat actors. Now I would like to pass the stage back to Tom to talk about some core functionality.
Thank you, Daniel. Okay, so we talked about Kazuar's architecture and its layers of encryption, obfuscation. Now let's see what other cool stuff it can do. So the 2017 variant of Kazuar had a list of 26 hard-coded commands. The variant we are talking about today has a list of 45 hard-coded commands. This is just one example of the efforts Turla puts into continuously developing their malware across the years. Now, as there are so many different commands, we organize them into different categories, so it's easier to track. It has a lot of capabilities to collect host data and forensic data from the machine. It can manipulate files. It can execute scripts any way you would like, VBS, PowerShell, JavaScript. It can create custom network requests. And one of its powers I want to highlight lies in its information stealing capabilities. Under Kazuar's information stealing capabilities, there are two main commands, which are referred to in the code as the steal command and the unattend command. By using the steal command, the attackers are able to target a variety of different applications to steal passwords. Dozens of different browsers. They can choose to steal bookmarks, history, cookies. And two noteworthy applications they target here are Signal and Git. And as you realize, they may contain some very sensitive data. The second command I mentioned is referred to in the code as the unattend command. And it looks like the attackers gave it this name because of the first option under the command, which is to steal unattended.xml files. These are Windows configuration files, which sometimes may contain passwords. But the really interesting aspect of this command is all the different cloud applications it enables the attackers to target. This really shows us the growing interest of threat actors in these kind of platforms. I mean, if an attacker can get access to Google Cloud or AWS, they now have access to tons of data, not to mention all of these sensitive servers. Now, there is another aspect of Kazuar that really impressed me personally during our analysis. When Kazuar is executed, it runs a task which is referred to in the code as first system info. We managed to extract the output of this task and see the log file that is being sent to the C2. And inside this log file, we saw that it sends operating system information, and system boot events, and user information, and hardware information, and more, and more, and more, and more. And honestly, all of this is not even half of the log file it sends to the C2. And because I can't fit it all on the screen, as you can see, I really tried here. Here is a snippet of the list of artifacts it collects from the infected machine to the C2. And the thing is, it doesn't even stop here. If the attackers would like, they could use a forensics command to query for various forensic artifacts from the infected machine. Or they could use the autoruns command to see if there is other malware that may be infecting the same machine. During our analysis, when I saw all of those capabilities, I said to Daniel that I feel that if Turla really wanted to, they can market Kazuar as a great incident response tool. Okay, so we see that it collects a bunch of data. How is it being exfiltrated? In order to communicate with the C2, Kazuar is able to use two main methods, which are determined by the injection mode Daniel talked about earlier. The first method is via HTTP. All the data is encrypted, encoded, and is being sent to the C2. Now, the interesting aspect of the HTTP request lies in the cookie. Kazuar uses a hard-coded cookie value which appears to not have been changed across several variants, across several years. So this is one of several very good detection opportunities we have to try and catch Kazuar. The second method Kazuar is able to use is, as we refer to it, proxy mode. Basically, Kazuar is able to send commands to other Kazuar implants in the network via named pipes. So let's try to visualize how a network infected with Kazuar would look like. We have our C2 that communicates with the Kazuar implant via HTTP. It can receive data, it can send commands. Now, if the attackers would like, they could use this Kazuar implant as a proxy to send commands to other Kazuar implants all over the network. So now the attackers are able, for example, bypass firewalls, as all of the communication is now internal. And we can't just find infected machines by searching for communication to a malicious domain. As again, most of the Kazuar implants do not directly communicate with the C2. So by using this approach, Turla is able to greatly enhance the stealth of their operations and remain undetected, sometimes even for years. Okay, there is one last aspect of Kazuar that I want to highlight, and it's anti-analysis. Kazuar is able to use several different techniques for anti-analysis. Some are basic and some are more advanced. First, we see that it specifically checks for a Kaspersky honeypot. It looks for the existence of several specific file names, both in English and in Russian. Next, it does some very common checks, like different analysis tools and different sandbox modules. And one very unique check that we saw is event log monitoring. Kazuar monitors events for several specific antivirus products, probably so the attackers can tell if they ever get caught by one of these products. And one very check that we found pretty cool or technique is anti-dumping. Kazuar's code is composed of a combination of .NET library methods and custom methods which were created by the authors of the malware. Now, when Kazuar is running, in memory, it goes over the references to all its methods. And if it is a reference to a .NET library method, it will keep it as is. But if it is a reference to a custom method, it will wipe the reference. So now if we will try to dump Kazuar from memory and analyze the code this way, everything is going to be messed up, and our job will be a lot harder. Okay, this is it for me geeking out about Kazuar's capabilities. So I'll pass the stage to Daniel one last time to talk to you about how to catch a Kazuar.
Thank you, Tom. So how do you catch a Kazuar? Because it's a really scary bird. But in terms of behavioral detection opportunities, so first of all, one technical thing we did not mention is that Kazuar stores its log path and its log files and chooses where to do it from a hard-coded list of directories. And these are really funny-looking folders. So this is just one detection opportunity to check for folder creation inside of one of these paths. And similar is the code injection part. So Kazuar also has a hard-coded process list eventually, and it will be injected to one of these processes. So if you have these weird folders, and if you can detect code injection in one of these browsers, you might have Kazuar running on your machine. So bad luck, I guess. And in terms of network communication, so Tom mentioned the hard-coded cookies. So Kazuar uses this string as a cookie from at least 2019, and I believe it might have been even used even earlier than 2019. And as other malwares, when Kazuar exfiltrates data, it obviously sends these really long post requests. And on top of that, they also use these randomly generated XML tags on top of these post requests. So if you combine these two, I think you can, even with a higher certainty, determine that this is indeed a packet of Kazuar. And finally, I would like to leave you with some key takeaways that we learned from our research and would like to share with you. So first of all, it is a state-of-the-art malware. It's a kind of a real-life cyber warfare tool, and as researchers, it was really, really cool for us to dissect it and analyze it and see like how the bad guys and sophisticated bad guys are using it in real time. Second takeaway is that similar to other developers, like both malicious and just like regular developers, the authors kept adapting to current technologies. So as Tom mentioned, this variant really focuses on stealing data from Signal and from cloud applications, and also from source control. So all of these technologies are really relevant for today, as you probably know. So the authors knew like where to go to and what data to steal. And finally, even though Kazuar is designed for stealth, as we saw in the previous slides, detection and prevention is still possible. Although difficult, it is still a detectable malware, so not everything is lost. That's it from us. Thank you for attending our talk. Of course, this was just the tip of the iceberg in terms of the malware analysis. I strongly encourage you to go and read our blog. And yeah, that's it. Thank you.
Thank you so much.